Now that we know the general form of the wave equations for both the electric field portion and the magnetic field portion, which you should recall those exist simultaneously, now that we know those general formulations, and we know how to relate the magnitude of the forward traveling portion of the E field component and the forward traveling component of the magnetic field, now that we know how to relate those via the intrinsic impedance of a medium, we can begin to do some calculations with E fields and H fields. So in this example, we have a medium. It's got an intrinsic impedance of 240 pi. We're given an equation for the E field. We're then asked to just write the E field in its phasor form. We want to determine the direction of the wave propagation. We want to find the phasor form of the magnetic field, and then write the time domain expression for the magnetic field. So let's start just with phasor form. The phasor form of electric fields and magnetic fields are almost exactly the same as what we've already done for voltages and currents. The difference is that we have to include this vector notation here. Notice that instead of just a bar here, this is an arrow above it. So we've got E of X, right? Because remember, the phasor form suppresses all time domain information, is equal to 480 pi. Nope, we get rid of the cosine. E to the plus j 10x, and it still points in the y direction. So that gives us the phasor form of the E field. Very simple. Measured in volts per meter. Remember, going to phasor form doesn't change the units. We're next asked to determine the unit vector in the direction of the wave propagation. So we have a little bit of information given to us in this problem statement here about directions. The first is that the E field is oriented in the a hat y direction. So if I were to draw my Cartesian coordinate system, where this is y, this is z, and this is x, what this is saying is that I've got my E field is oriented in the x, or is in the a hat y direction. Well, what other information do I have? Well, remember, this is the variable is the direction of wave propagation, and so this is an E field that is propagating in the x direction. That also means the H field is going to be propagating in the x direction because they propagate in the same direction. The direction of wave propagation is x. So if we were to draw that, the wave that is propagating a hat rho, that's the, and I just mean this to be in the the positive x direction. So the answer to this one is by inspection. Oh, excuse me, I got that wrong. The signs are the same. It actually propagates in the negative x direction. Like that. Right. So this is a hat rho in that direction right there. My apologies. So, and the reason I knew that is because the signs on the omega t and the beta x term here are the same, and we know from actually the first unit that we did on wave propagation is that if the signs are the same, it's a negative traveling direction right there. So we've got this thing traveling in the negative x direction, where the E field is pointing in the positive y direction. It's not asking us to do that in this point, but right now we could go ahead and figure out what direction the H field is propagating in. And to do that, one way to do that is to use the right hand rule. Take your thumb and point it in the direction of the E field. The index finger then extends in the direction of the H field, and the middle finger extends in the direction of the propagation of the plane wave. And so in this case, what I would have to do is take my thumb and point it in the direction of the E field, and my middle finger and point that in the direction of the a hat rho, and then my finger, my index finger, will then point in the direction of the magnetic field orientation, which is going to be in the minus z direction for this case. So hopefully when we do the math, our result is that we get an H field that points in the minus z direction. So anyway, so now we've formed the phasor form of the E field and the unit vector in direction of the wave propagation, which was just a hat rho is equal to minus a hat z. So how do we determine the phasor form of the E field? Well, first we just got to figure out what the magnitude of the E field is, and H bar is equal to 1 over eta times a hat rho crossed with the E field vector. And what we can do is we can substitute our givens in here. So that's 1 over 240 pi ohms times minus a hat x. And we'll cross that whole thing with 480 pi e to the j 10x a hat y. So this is the cross product we have to form. And that is h, I'm just going from here over to here, h is equal to the determinant of a hat x. The first part of that is this cross product. This has got a minus 1 over 240 pi. And it has 0 for a hat y, and it has 0 for a hat z. And this one only has a component in the a hat y direction. So that's 0, 480 pi e to the j 10x, and then 0. And so what we see is the result of this is that we get a hat x, 0 minus 0, a hat y, 0 minus 0, and a hat z, minus 1 over 240 pi times 480 pi e to the j 10x minus 0. So that's just going to be a hat z times minus 1 over 240 pi times 480 pi e to the j 10x, all minus 0. So if we simplify that, that is 480 pi divided by 240 pi is 2. It's minus 2 because of the minus sign right here. So minus 2 e to the j 10x a hat z, which is the equivalent of 2 e to the j 10x minus a hat z. And that's going to be in amps per meter since it is a magnetic field. And so that gives us the phasor form of the E field, which was the third thing we were asked for. Now we just have to translate that over to the time domain. So h bar is equal to minus 2 cosine of omega t plus 10x, pointing in the z direction, amps per meter. And so that's the end of the problem. And just the last thing I'd like to point out is that initially we predicted that h has to point in the negative x direction, and indeed it does right there. So it's consistent with the right-hand rule.